Hi everyone and welcome to the video on section 7.2 volumes by disk method or washer method. The objectives for this video are 1. Find the volume of a solid of revolution using the disk method. Number 2. Find the volume of a solid of revolution using the washer method. Or number 3. Find the volume of a solid with known cross sections. Now for the last one, what's going to happen is that we're going to make cross sections, cuts, perpendicular to either the X or Y axis. And when we make those cuts, the face of that cut is going to be something like a triangle, could be a square, rectangle, could be a circle, but more than likely it will be one of these other figures. And we're going to have to find the volume of that particular solid as well. Let's start out making sure we're all on the same page. A solid of revolution, that is formed when a region of a plane is revolved about a line. That line is going to be called the axis of revolution. And that axis generally, for a lot of the problems you're going to work with, that axis is either going to be horizontal or vertical. And a lot of times it's going to be either the x-axis or y-axis, but please keep in mind that that axis can change. It doesn't have to be the x-axis or y-axis. We could revolve around the line y equals -2 if I wanted to, or I could take a region and revolve it around the line x equals 5. Those would all be possible things that could happen, and we'll be looking at how we adjust these formulas that we're going to be working with coming up soon. Now the idea behind the disk method, what we're going to do is we're going to take a rectangle. And if I take a rectangle and I rotate it around the x-axis, what I'm going to generate is I'm going to generate a figure like this. It's going to be a very skinny cylinder, if you will, or what we call a disk. Now to get an idea of what that looks like, you could go and just take a look at like a coin. Okay, it's very thin, but you have a circular face on it. And that's really what we're looking at here. And these are skinny cylinders or a disk. And the volume of a disk is found by the area. Any disk is going to be the area of the base, which in that case is a circle, so the area of a circle is pi r squared, times the height. Now in this case, the height is delta x. So when I look at this particular situation where my height of this rectangle here is y, the base is delta x, the volume of this particular disk, that volume is going to be pi times y squared, because that's going to be the radius, times the height, which would be delta x. Now let's take a look at a couple pictures, and these pictures can be found in your book. What we're looking at here is I have a plane region here in blue, and I have a rectangle, what they call a representative rectangle, and I'm going to go through and I'm rotating this region about this axis that I have down here, my axis of revolution. And when I do that, this right here is actually going to form this solid you see right here. And you'll notice that this rectangle has a little bit sticking out over there, and that's why it's yellow here, and then you have the blue in there too. And what happens here, as I go through and do this, when I create that solid, I go through with my different rectangles. And I could take these rectangles that I have, let's put some more in. I could go here, 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 and I could go backwards too, there, and let's say right here. And I can take those rectangles I now have and I can revolve those around, and I'm going to create a series of disks. And those series of disks are going to look something like these. And I can go through and find the volume of each individual disk and add it up, and that's going to give me a decent approximation for the volume of this solid that we have right here. And of course, like we did when we were dealing with areas and with Riemann sums, in essence, this is a kind of a Riemann sum. What I'm going to do is that as delta x gets smaller and smaller, we're going to get a much more accurate approximation. And as delta, as that change in x gets really, really small, we're going to actually end up with a definite integral that we can use to find that volume, and that is going to be known as the disk method. So when we look at that, what we do is we represent r of x, or r of y is our radius. And when we work with this, when we rotate around, we can either do it around a horizontal axis or a vertical axis. And we're going to take, it's going to become the pi times the integral from a to b of the radius function squared dx. Okay, now you should notice, remember that this is my radius. Pi times the radius squared is the area of the circle, and dx represents the base. So pi times the integral from a to b of r of x squared dx, that is going to be our volume formula for this is the disk method when I'm taking around a horizontal axis. When I'm taking around a vertical axis, in that instance, what has to happen is I have to go through, number one, my radius is going to be a function of y. So I've got to look at that as an x equals, and it's going to be pi times the integral from c to d of that radius function squared dy. Notice that we do have our representative rectangles in each case here that we can use to kind of get a feel for. What's changing on this one here is the y values, which is going to be changing there is the x. Let's take a look at an example here. We're going to actually do this same problem in two different ways. We're letting our region be bounded. It's the first quadrant region in the parabola 4 minus x squared. So the region that you see in pink is the region that we're going to take. And we're going to take this thing first around the x-axis. So I want to come up with an integral that I can use to find the volume of that particular solid. Well, in this case, my radius is actually going to be the function itself. So in this case, 4 minus x squared will be the radius. And so my volume here of that solid, when I go around the x-axis, I integrate with respect to x, it's going to be pi times the integral from, in this case, 0 to 2 of my radius 4 minus x squared, make that x squared, that thing squared dx. Now to go and evaluate this, I would need to go and expand that. So that would be equal to pi times the integral from 0 to 2 of, when I multiply out 4 minus x squared, that thing squared, I will get 16 minus 8x squared plus x to the fourth, and I would do that dx. And at that point, it's just the power rule to integrate that, and then using the fundamental theorem of calculus to find the volume at the end. What I'd like you to do right now, I'd like you to pause the video and actually go through and do the integration and compute that volume. Welcome back. When you did this one, you should have come up with the pi times the integral, or pi times 16x minus 8/3 x cubed plus 1/5 x to the fifth. And we're going to take that from 0 to 2. And when I go and do the fundamental theorem of calculus on that, I will come up with 256 pi over 15, and that would be units cubed because we are talking about a volume. Now let's take a look at what happens when I take this around the y-axis. Now when I take it around the y-axis, I have to have my equations here at my radius equation as x equals. So again, my radius is still going to be this curve, but instead of y equals 4 minus x squared, I'm going to let that be x, let's put it as a pencil, x equals the square root of 4 minus y. And so now in this case, when I take this, I'm revolving it around now the y-axis, I'm going to get that volume is going to equal pi times the integral. Now this time the y, because we're going to be integrating with respect to y, the y values go from 0 to 4 of my radius function, which is the square root of 4 minus y, that thing squared dy. So it's going to be pi times the integral from 0 to 4 of, when I simplify that, that is going to be 4 minus y dy, which equals pi times 4y minus 1/2 y squared. And again, we're going from 0 to 4. So when I do that one, that's going to be, obviously when 0 goes in, it's going to be 0. So it's going to be pi times, when I put in 4, I get 16 minus 8. So the result is going to come out to be 8 pi. I didn't have to worry about the 0 because when I did that lower limit, it would end up being a minus 0 there. So the result is 8 pi cubic units. Now let's take a look at what's called the washer method. And the idea behind the washer method is I'm going to take a region, I'm going to revolve it around a horizontal or vertical line. And when I do that, I'm going to have, like if I take this region here and I revolved it around the x-axis, what I'm going to generate is a disk that is going to have a hole in it. And I need to find the volume of that solid. Well, in this case, notice we have f of x is this line and g of x is here. So when I take that around, when I do that, I'm going to go through on this. And if I go through it, if I want to just deal with f of x, I could find the volume of the solid generated by rotating f of x around the x-axis, and that would come out to be pi times the integral from a to b of f of x, that thing squared, dx. Now, the problem that I have though is I don't need all of that. That's going to be everything here. I just want this part. Well, the part that I need to cut out, this portion, is going to be, it can be found by taking my lower bound, my lower function here, g of x, and rotating it around the x-axis and taking that volume that's generated there and subtracting it from what I get from here. So what I'm going to do to find this is I will then take minus pi times the integral from a to b of g of x, that thing squared dx. And now properties with integrals, this thing can be written as pi times the integral from a to b of f of x squared minus g of x squared dx. And this is what's often called the washer method. The way you want to think of it, what the book uses is pi times the integral from a to b of capital R of x would be the outside radius squared minus little r of x, which would be the inside radius squared dx. So this part right there is outside radius. And this part right there, that is the inside radius. Please note on this that right now I'm just setting this up for rotating around a horizontal line. When I do a vertical, if I was going to go around a vertical line, the x's would be y's and I would be integrating with respect to y. Here we have two problems. I've already worked them out for you so you can kind of follow along with what's happening here. In this case, we have a region that's going to be bounded by y equals x, or the cube root of x, sorry, and y equals x squared. So here's y equals x squared, here's the cube root of x, and here's our region. Now, in this case, they do have, we're not told any x or y values, and so I know I am looking for the intersection points, and they happen, these two functions happen to intersect at the origin, 0, 0, and at 1, 1. So that's why when you look at these two problems, you're going to see the same limits of integration. Now the first thing we have to do is we're going to take this and we're going to rotate it around the x-axis. So this portion here, when I look at that, when I try to go through and determine my outside radius and my inside radius, it is with respect to the axis of rotation. So when I'm rotating around the x-axis, I know that the portion, the boundary of the region that's furthest away from the x-axis is going to represent my outside radius. So in this case, that would be the cube root of x. The boundary of the region closest to the x-axis is going to be my inside radius, which in this case is x squared. Please note, if you are ever in doubt, start from your axis of rotation underneath that region and go up. The first one you come to is going to be your inside radius. The second one you come to would be your outside. So in this case, because my outside radius is to the cube root, which would be x to the 1/3, this is going to be pi times the integral from 0 to 1 of x to the 1/3, that thing squared, minus my inside radius, which is x squared, that thing squared, dx. When I simplify that, that's pi times the integral from 0 to 1 of x to the 2/3 minus x to the 4th. So that's pi times the integral of this expression is 3/5 x to the 5/3 minus 1/5 x to the 5th. And I'm going from 0 to 1. When I actually evaluate that, it will come out to be 2 pi over 5 cubic units. Now what I'm going to do is I'm going to take this region and I'm going to rotate it around the y-axis. Well, the first thing again that I have to do is that these equations here have to be written as x equals. So y equal the cube root of x would mean that x is equal to y cubed, and y equal to x squared becomes x equals the square root of y, which I know is y to the 1/2 power. And so when I want to find the volume of the solid generated by taking this region here and rotating it around the y-axis, what I'm going to get is pi times the integral from 0 to 1 of y to the 1/2. In this case, my outside radius is this portion right there, which is y to the 1/2, y to the 1/2 squared minus y cubed squared dy. And so that becomes pi times the integral from 0 to 1. When I simplify those, that's y minus y to the 6th dy, which is pi times 1/2 y squared minus 1/7 y to the 7th. And when I go through and actually go and calculate that definite integral, it will come out to be 5 pi over 14 cubic units. Please pause the video right now and make sure you're comfortable with how I set this up and anything that I did in these problems. Now let's take a look at what happens when we change the axis. Okay, now remember here that this portion right there is the outside radius, this is the inside radius. It does not necessarily mean that we don't necessarily have to have that outside radius have to be one of these functions. It could change, and that's going to be based on changing what happens with the axis of rotation. Now I'm just going to look at this in terms of rotating around a horizontal line, so that's why we're just looking at y equals -1, y equals 2, and then we'll look at a general y equals L. In this case, when we work with that problem, please note that these up here, what we've done so far, when we use these as our outside and inside radius, our axis of rotation was the x-axis, which happened to be y equals 0. Now the first thing I want you to notice here in terms of this problem right here, if we rotate around y equals -1, what that means is that my radius is actually, since I'm going to be rotating around the line y equals -1, somewhere right around here. Actually be about over here more. But since I'm going to rotate around y equals -1, what I'm going to see then when I do that is that my radius is actually going to be bigger. My radius at any given moment is going to be 1 more than it is when it was rotating around the x-axis. And so for this particular problem, my definite integral, if I'm rotating around y equals -1, my outside radius is going to be the cube root function. My inside radius is going to be y squared. And it's going to involve y squared. So it's going to be pi, a definite integral to solve this one would be pi times the integral, again from 0 to 1. Now my outside radius is going to be the cube root of x plus 1. that thing squared, minus my inside radius is going to be x squared plus 1, that thing squared. And when I do that, that is going to be with respect to x. Please notice again that because my radius, I'm rotating around y equals -1, my radius is now 1 unit longer than it was before. Thus, we have the plus 1. Let's take a look at what happens when I rotate around y equals 2. Now, y equals 2 is going to be up here. Now, the first thing you should notice when we do that is that now, because my axis of rotation is up here, we are looking at my outside and inside radius is going to change. Which one is going to be involved? In this case right here, when I'm rotating around this one, my inside radius is now going to involve the cube root, and my outside radius is going to involve the x squared. And so, when I do that, it's going to be pi times the integral from 0 to 1 of, now technically, because we are above here, I know, and a radius is a distance, this is going to have to be my inside radius, or my outside radius, is going to be 2 minus x squared, that thing squared, minus, here it's going to be 2 minus the cube root of x, that thing squared, dx. Now, the question often comes up, do I have to necessarily worry about that? Could I have put in x squared minus 2? Well, technically that wouldn't be correct because a radius, again, is a distance. But if you did that, you're not really going to see any change. It's not going to cause any problem because of the fact that you're squaring it. So even if you wrote in x squared minus 2, when I squared it, the result would still be positive, and it will still work out. That's why you're not going to see too many. They don't get too picky about that when you work with these. So when I look at this, when I take it around y equals L, really what's going to in general happen, because now we have our, now I can't say where L is on this graph, so I'm just going to use the R of x for my, the one function for my outside, one for my inside. So we'll have like f of x is the outside, g of x is inside. It is going to be pi, the result will be pi times the integral from a to b of f of x minus L, that thing squared, this will be my outside radius, minus g, it's going to be g of x minus L, that thing squared, dx. And again, remember this portion right here, this portion right there, that is my outside radius, r of x, and this represents my inside radius, little r of x. Again, I have to reiterate this, that this is really looking at just for horizontal axis. This is, there is something similar that would happen with a vertical axis, and it would behave the same way as it does with these problems here. Now let's take a look at a problem where we're dealing with the volume of a solid with a known cross-section. In this case, what happens on this? When I'm finding this volume, to find a volume, I need to integrate an area formula. And so what's going to happen is that when they tell me what shape the cross-section has, I'll be able to determine an area formula, and then I can go and integrate that. And again, if we are looking at a volume, if we're looking at cross sections perpendicular to the x-axis, this is going to be we're going to integrate with respect to x. If we were perpendicular to the y-axis, we would be dealing with integrating with respect to y. So in this case, what I have is a region that's bounded by y equals the square root of x, y equals 0, and x equals 4. And that's the base of a solid with isosceles right triangle cross sections. And these are when it's perpendicular. I forgot to write it in there, but it is when the cross section cuts are perpendicular to the x-axis. They want us to find the volume. So what you'll notice here is the curve. we're going to 0 to 4. And what I've tried to do is draw in those cross section there. So we do have an isosceles right triangle, so I know this length and that length are the same, and we see that it is a right triangle. And so I want to find the volume of that. Now the area of an isosceles right triangle is going to be 1/2 the base times height. Well, the base and height are going to be the same, so it's going to be 1/2 of y squared. I'll use y because when I look at the base of my solid, it is lying here, and so the length of the side is just going to be the y coordinate of those points. So I'll use the y squared. And I know in this case y equals the square root of x. So when I set this up, this is going to be the integral from x is going from 0 to 4 of 1/2 of the square root of x, which is y, that thing squared, dx. So I have 1/2, I'm going to pull that 1/2 times the integral from 0 to 4. When I square that, I get x dx. And so the integral of that will come out to be 1/2 times the integral of x squared is 1/2 x squared. So if I multiply that by 1/2, I'll get 1/4 x squared going from 0 to 4. And evaluating that, I will get, that will come out to be 4 cubic units. This now does conclude my video on volumes with disc, washers, and cross sections. We will be taking a look at more problems like this in class. To give you some more examples, we'll also look at how we adjust the formulas for the washer method when we're going around a vertical line, or as we just did with this, when we are going to be doing cross sections perpendicular to the y-axis. So we'll look at how that changes as well. So with that, I hope you are having a good evening, and I will see you in our next class.